Welcome to springlib.
Um, Once again, we have a new problem, and this time we still have a diffraction grating, and it has an opening, and the opening happens to be of width 1.8 centimeters. So this opening happens to be 1.8 centimeters, and there's a beam of light that's coming through, and there's diffraction that's obviously going to take place on that beam of light. And it so happens that the gap has gratings within the gap, and these gratings provide 1,400 lines per centimeters. So you can imagine what's happening right here. We do have 1.8 centimeters, and then think about having 1,400 lines per centimeters going through. The wavelength of this light is lambda, is equivalent to 450 nanometers. That's your lambda. The beam of light, it's a beam of light that's centered on 450 nanometers in terms of wavelength. And this point right here, as it goes through, it hits the diffraction grating at a perpendicular angle. As you can see, that it's 90. That's the information that we're given in the problem, and we want to find the minimum, or the smallest, the minimum lambda difference. Remember, lambda is the wavelength, so the minimum lambda difference, the grating resolves in order 3. So that's kind of what we want to find out in this particular problem. We want to find out the minimum that it can resolve. So, once again, we have a new problem, and we're seeing it's still a diffraction problem. We're seeing it's a diffraction problem, and we want to find out what's the minimum that we can still have. We want to find out what's the minimum that we can still have. So if we have all these pieces of information that we're given, we're going to jump and start solving the problem. And we do have to make some changes in terms of lambda. Remember, lambda is the wavelength, which is 450 nanometers, and the width is 1.8 centimeters, and the line density is given as 1,400 lines per centimeter. And given that we have 1.8 centimeters, we can always get the total number of lines n, which is just multiplying the 1,400 by 1.8, and that gives us 2,520 lines. That's the total number of lines on the diffraction grating. That's the total number of lines on the diffraction grating. Because now we do have 2,500. We have 2,500, and that's what we're working with in this particular problem. So for the third order, order 3. Order 3, that's the order we're dealing with. The resolving power. The resolving power is the average lambda divided by the change in lambda, and that's just n, which is number of lines, times the order, which is 3. This is order 3, m equals to 3. And so the average lambda is 450 nanometers, and m is 3. N, you can recall, is 2,520 lines. We did solve for that. So remember, we wanted to find, going back, if you can recall, the smallest wavelength difference. So that's, or the minimum wavelength difference. So that's just our delta lambda. And so delta lambda is delta average all over nm, which becomes 450 nanometers, all over 2,520 times 3. And so delta lambda is going to be equivalent to 0.0595 nanometers. That's what our delta lambda is going to be in this particular problem. Of course, you can change that to 5.95 times 10 to the negative 11 meters. So once again, I hope you did enjoy the problem. It was a grading problem, and the initial pieces of information that were given included the beam centered at 450 Newton nanometers, meaning that if you have a beam and it has an average wavelength of 450 nanometers, and then of course you have 1,400 lines per centimeters, we can get the total number of lines, since the opening is the same as 1.8 centimeters. That's the opening. The opening is 1.8 centimeters, and we get 2,520 lines at order 3. We can get the difference, which is delta lambda 450 over 2,520 times 3. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.